Yeah, okay, so welcome everyone to this Coffee and Learn session. Today we will talk about online labs, how to teach with them, how to set them up in a way that they bring about students' learning. I think this is, totally relevant in these COVID times. So in this session, I think that we are lucky enough to have two people with much experience and expertise in this field. We have Denis Gillet. He's a senior scientist and head of React Group of the School of Engineering and also member of the Swiss Tech Collider Executive Board. He will give us an overview of what online labs are and how they, generally are used nowadays. And then we have Christophe Salzmann. He's, among other things, a lecturer at the School of Engineering, researcher at the Automatic Control Lab, and operations manager at DLL. He will talk about his teaching experience with online labs at EPFL. Okay, so we thank you both for your willingness to contribute to this session, and we can start with Denis. So the floor is yours.
So, good afternoon, everyone. Nice to see you all. I will give a very short introduction because most of the core information will be provided by Christophe. So we have this common title about teaching online laboratories. I would rather say it's about enabling learning with online laboratories, but we have first to just try to introduce what we mean by online laboratories. It's the main idea of my introduction. And then Christophe will present how we, in fact, implement online remote laboratories, which is one part of lab. So we have this distinction in online laboratories. Typically, we talk about virtual labs when we talk about providing simulation of laboratory equipment to students, and they might be online because we provide access through a web page to the simulation to enable more easy update of the simulation if necessary. And the remote labs is completely different. It's really about providing the ability for the students to operate a real physical lab, which is located at distance. So in terms of technical challenges, it's pretty different. In terms of also of teaching, it's a bit different because when you use virtual labs, it's not really challenging for the teacher to introduce that in a class because simulation is always there. When you introduce in your teaching access to physical equipment, you have to really make sure that it is operating well during the time when you connect to it. So it's a bit more challenging, and sometimes teachers have been reluctant to do that. Anyhow, we are running big projects at TPFL at the European level to promote the education in science and technology, and especially to raise the interest for kids for science and technology through providing access to online labs for primary and secondary schools. So it's a big Go Lab project we have on that. And we have also a project where we provide access to virtual labs to students from developing countries. In developing countries, we do not even try to access real physical lab at distance just because mainly of the quality of the network, which very often do not enable them to do teleoperation. We have, and you see on the side, for example, the website we offer to primary and secondary schools, where you see at the bottom that we are offering more than 800 online labs, and a small fraction are remote labs, and a bigger fraction are virtual labs, which means simulation. And we also offer data sets. It's another way of, doing, or using data from real experiment and to work on them. EPFL, we have been together with Christophe involved in a IEEE standardization committee to standardize the access to remote laboratory. So I will talk very quickly about that, but I promise myself not to speak more for more than 5 minutes, so I will try to be short. So when we discuss about remote labs, so again, remote access to physical laboratories, we have to start from the initial conditions, which are students doing an experiment in a physical laboratory, the university premise, like on the picture. So you have typically a group of students interacting with the scientific equipment, and to interact with the scientific equipment, obviously they have instrumentations to take measurements. They can see the full installation, and they might have actuators or way to modify the configuration of the experiment, or to fill tank, to move robots, to increase temperature, things like that. So we need those devices. So in some cases, we want to enable the operation of that equipment at distance. So this is where when we start to talk about remote lab. And the challenge is really to provide the same quality of interaction for the people when they work at distance compared to the situation when they operate directly the equipment. So obviously the challenge is on the side of the equipment to enable remote access. So it's mainly typically turning the instrumentation into web services that the people can connect at distance. On the red line, there is the internet for enabling remote connections, and you have to provide ways to the students to observe and to manipulate at distance the equipment. So the motivation to do it at distance could be obviously before, so COVID, it's obvious that we don't want the people on campus, but before we were already implementing that just because of the increased number of students. For logistical purpose, it was impossible, for example, at TPFL to have 300 students at the same time in labs, which were typically designed when they build campus for 20 or 30 people. So when you provide access, it's more easy to remote access, then people can connect when they want. And it's also more interesting from a pedagogical point of view that you go to the lab when you are ready to do the experimentation and you have already studied the things. When we work with developing countries, also a way to provide access to students to equipment they might not have available in their country. And the distance is often not only between the students and the equipment, but it can be between the students, because we all know the benefit of doing learning activities in teams. And when you are at distance, you have also to provide or to enable interaction between the students if they are not at the same place, and also with the tutors or the teaching assistants. So there is a lot of challenge associated with those remote labs, but they are very useful to implement, to provide more opportunities for the people to experiment and then to learn through hands-on activities. So just quickly, what we have done in the standardization committee of IEEE is to define and try to standardize a few layers of communication, and it's related to what I presented. So at the bottom, we have a layer where we describe the hardware and the software of the equipment and the instrumentation. Typically, there is nothing to standardize at that level because the sensors, actuators, instruments you are putting on an equipment is really depending of the type of experiment you have. But when you try to provide web access to those instruments at distance, then we add the layer number 1, where we define the laboratory as a service with standardized web call, enabling the people at distance, to, for example, request the measurement of a given sensor or change the configuration of a given actuator. So most of the standardization what was done at that level to enable the people to build their own software for accessing an experiment and doing the manipulations and the observation they want. Typically, obviously, the students will not call directly the web services. So at the level number 2, those calls are embedded in software client, which are typically the interface used by the students to manipulate the experiments. And you will see examples from Christophe. And for a pedagogical point of view, you don't just use a small interface to operate an equipment, but you integrate those things in a MOOC platform, in a learning management system, so broader, solutions to bring the pedagogical value and the structure on the activity. So all those layers have been standardized, and obviously authentication is very important to enable collaboration, to enable people to collect data, for example, and do activities on that. And especially because we connect to physical laboratory equipment. So you don't want anyone to, harm the equipment and to destroy your experiments. And on the left-hand side, we have also, we are trying to collect data about the activities of the students, respecting the privacy. So there is, side, flow of information which are important. So what was interesting, it's the definition of those 4 layers took us 6 years at the level of IEEE. So I could give you a talk on the joy of participating in a standardization committee, but it will be for another talk. But this was a very general introduction about the remote labs, and Christophe will show you what he has done at EPFL. So if you have questions on that, otherwise I pass the floor directly to Christophe.
Well, maybe if someone has a question, they can pose it now. And if not, we'll go to Christophe. Yeah, okay. You're muted, Christophe.
Unmute. Okay. You hear me now?
Yeah.
Okay, perfect. Sorry. I'll talk about online remote labs. And the plan for today, I will talk about the current solution you have to provide you lab you normally do within EPFL at a distance. And then that's the current solution, and also what it takes for you if you decide to put a new lab online, and where to start, and what are the pedagogical aspect you have to follow and what you could do. Then I'll go through our example for the MOOC with a hands-on session for the control system course, then some evaluation we did with the class, and some conclusion. So first example you have, so you could have like an online simulation, as Denis was referring. So it's not a remote lab, but it might be very useful if you have, with simulations. A good thing is that you can play with a lot of parameters. You can, accelerate or decelerate the time. You can also simulate destructive process, like on this plate. I'm not sure if you see this applet here on top right is like a meteorite collision with Earth and with varying parameters. You can also, for example, simulate the glycemic issue and what you have as a diabetes. So you can play with all these aspects without killing the human who has the liver and this issue. You could have, very nice 3D VR simulation of real process. So it's very easy to modify things and test various parameters. And here you have on the left the typical tools that we use when we teach control. And modelization and simulation are very important tools and skills that every engineer should master because it's tools to explain the world, and a lot of students are required to use these tools and before playing with the real systems that I will show you in a minute. But there is always a question, so why don't we use only a simulation everywhere? And basically, you have to learn how to model a system and how to do a simulation. So simulating a simulation is you kind of miss the point. So it's not one instead of the other, is that you have to be able to master both. You have to master simulation, and then you have to master, playing with the real setup and dealing with things that you don't see in simulation. And then one another alternative you can use for labs when you have to do it online. I took example for my colleagues, like for example François Galère, where he had recorded video, and then you have the time on the left, and then the students can do measurement and infer some, I don't know, viscosity factor or whatever. I don't know exactly what they have to do. For another experiment here, which lasts probably 10 or even more minutes, they recorded measurements and a video of the system. You can play the video faster. They have a bunch of these video, and then at the end with the measurement, student has to infer some values or identify some parameters. So there is on the EPFL switch tube, there's plenty of video. This is for the uh, uh, as a material department. I think it's they put the resin within this system, and it has different factor if it's saturated or not. Okay, I will go through the next one. Another tool that was used during the COVID is, for example, in EE, they had this 3 motors control. And so what they had is that they had a computer here which controls the system and everything is connected. So this computer is used locally, but you can just imagine that, okay, you got a computer, everything is ready to have remote desktop access to this computer, which is fine. You could do this setup from a distance, at the distance, but the issue is that you need someone to turn this motor on and off, all this equipment, also to wire it if you have to do some changes. So basically you have remote hand with a human that is close to the equipment, and okay, it's doable, but it's not very efficient, I would say, because for one student you need one human within a lab, so it's not really a win-win solution. The alternative, what they did is that they set a bunch of computers connected to remote equipment. They provided various signal, and they tell the students, according to a table that you see below, when they have to come, on which equipment they have to come, and they could do remote experimentation through remote desktop. So basically it's like you had a remote keyboard and a remote screen. They could do whatever you were doing locally, but this without visual feedback, so they didn't really have all uh, the same user experience as if they were very close to the system. Another alternative that was one of the first experiments we put online through a MOOC. So it's a fluid mechanics example. I'll show you a demo at the end. And it's a big equipment, it's 4 meter long, and we developed a web application. And this web application, we, for example, put it within a MOOC, the edX MOOC of François Galère and Christophe Salzmann, and it was integrated as an iframe, and then we had question on this MOOC. So, and then we managed everything, and since it was a web app, it was very easy to uh, add within edX or any other MOOC you may like, or within, for example, Moodle, it's also doable. So the question is that what does it take to put your experiment online? So you have, for example, an idea of say, okay, I would like to put my new experiment online. So where should I start? What should I do? What are the right questions to be asked before starting? So the first one is that, does it make sense to put this experiment online? What do I want to show? And is it doable? I mean, you have to assess what it will take to do it. So, for example, the first thing is that since you're putting it online, you will observe some phenomenon, and you have to see if it's visual phenomenon. Is that sound? Is that the temperature? What are the sensors you will have? How you will act on the system? And what's the dynamic of the system? Does it take, are you observing a phenomenon that lasts hours or days, a week, or is it a nanosecond, or is it in the order of the second to a few minutes? And that's mechatronical experiments that you have on the right. And these ones are very well suited for remote experimentation. But on the left, for example, you have a fish population grows, and then it takes week for to see the fish growing, so maybe it's not adequate, and then maybe it's better to have a simulation where you can change the initial condition, and maybe there it makes more sense instead of having live interactive experimentation. Okay, it's nice to watch an aquarium, but maybe it's not the aim of this experiment. uh, so the question you should ask yourself when you start is that, does this experiment already exist? If yes, it's already a good starting point. The next one is that, does it run autonomously? Which means, do you need or not to have a human to prepare the setup, or maybe make it back once the experiment is done? Is it reversible? So do I need to put more water in the system? Do I have to manually set it up back in a initially known position? And do I already have measurement point or actuation on the system so I can act it remotely? So if all this question is yes, you are quite in good shape to put it online, and it start to be easy. If some are known, you will have maybe to uh, extend your setup in order to make it, for example, autonomous and reversible. So here are the four stage of, and a small example here, that was the previous electrical drive we used to for the control system course, and the aim was to mimic what you had on the left, on the right angle, and you should have it the same thing on the left. So on the right you see, I don't know if you see my pointers or not. If I do, oops, sorry. Here, so you have an analog controller, a signal generator, and the signal was seen on the oscilloscope. And okay, it works perfectly, but you had to be there. So the next step was to put the instrument. So we replace the analog controller with a computer program. And also you see that here there is no cable connected anymore. And now we replace this by a signal generator, a virtual one. And then through the user interface, we could act and modify the system. So here for this system, if you have if you had a remote connection software, you could connect to the system and control it remotely, but you have no visual feedback. So the next idea was to put a webcam in front of the system to film it, and then we were completely autonomous. So we had visual feedback plus remote access. And in the last century, we started to have live demo during the course, where the teacher could show, videos of the system. You see it a bit in the back. And so he could do live remote experimentation while giving his class. So it has a big impact there. And the next step is to have a specifically designed equipment that is, autonomous. It is uh, meant to be run remotely. It's robust to students, so that means students cannot break it. We had, with the previous one, we saw that students were trying to break the system, which is part of the learning process. and we have like 25 of this equipment, and it's accessed through a web interface via MOOC. And it could be a MOOC, it could be LMS like Moodle or Grasp, because we use LTI integration, and we design some software package that are available. So if you're interested, just ask me, and it's a matter of day to adapt your system normally. And of course, with this system, we have the web interface following this IEEE specification, which means if your system follow this specification, you can design the web interface you like. So we say, okay, my system provide you this information. You can talk to my system using this kind of API, but you're completely free to design your own user interface. So once you put your setup online, it's great, but you just halfway through. So next step is to really provide a sound user experience at a distance for the students. So that means you will have to resync you handle session. You have to think about the user interface you want to provide the students to when you access the system. You have to rethink the curriculum, the timing, the pedagogy. You have to rethink a lot of things. And then if you do it well, you could also use you could also integrate with value-added environment like MOOC, as we did, or LMS and everything. And you have to also test and evaluate. It's not a one-shot setup. It's through improvement that you start to have a valuable experiment. So question you should ask, what kind of interface you provide. So now the client application must be a web page using HTML5, WebSocket, JavaScript, CSS. You could do like a regular application. It's already complicated enough to have a web page that runs on all the browsers that are available on all the platform. But now the technology is there, so there is no point in using another technology. So we try Flash, we try Java, we try a lot of different things, but this is gone. We should just get rid of all these things. It's already complicated enough to have a web application that runs everywhere. And then also, since students will do the experiment remotely, they will be alone. So one of the issue we had, especially this semester, is that how do you engage students to work remotely? It was a difficult task. So we tried different things. Once was to force them to work in groups. So basically, we form groups for them, and then you say, okay, this afternoon, like Tuesday afternoon, you go from 3 to 5, and you log within Zoom with your group, and you have dedicated rooms. And then from there, you can work on the TP questions. So this works quite well. Um, it's too early to get a very good feedback on a system. We haven't finished to grade the copies. Another thing we try is to give challenges to students. That was for another course, and there was a regular question plus the challenges. What I found out, unfortunately, is that the students who take the challenges are the good students who are already done with the other exercise. So it was not, I mean, it was good for the one who took the challenges, but not for all. And the idea is to take the whole class and not doing exercise just for the best students. Also, we added some open questions, like question where there is no right or wrong answer, but to make them think. And I think this is very important, and we'll go further in that direction, but it takes a lot of time to assess what the students reply. And also at the end they wanted to have a solution for this open question, and that was, yeah, a bit disappointing. They were quite perturbed by not having a yes or no answer. And So how do you handle like 400 students? Like I had this finishing semester, so we did a lot of Zoom question answer session. We used Piazza. Previous semester, I did a lot of support through email, which was a real pain. I mean, way too many questions through emails. And so how do you support more students if you have more students than experiment? I'll show you some solution we do. We have a different control observer mode. We can queue reservation. We can provide additional awareness to the students and some gamification process. And now it's time for a real demo. So I'll switch to the MOOC. So we have a MOOC on the control system. So we're teaching the students control. It's me with a video explaining. I mean, it's a MOOC. We have some repetition, some question, and I will go here. Which one? Okay. So now here I'm connected to one of the setup I have. I have here, if I update the list here, I have a bunch of setups here, and I can control my setup. So here on the left, I have an oscilloscope window. So the measurement I have are sent directly to my system. Here I have a visual feedback of the system. Here I can, on the top, I can control the system. I have a signal generator. So for example, here, I can change the signal I apply to the system. I can change the amplitude. I can do a lot of different things on a system. And then here on the right, I have the controller, and below I have some uh, signals I can change. I have the possibility to clear the buffers display. I can save the measurement I have in edX. I'll explain you this in a minute. I can save it on my hard drive, and here I have some additional info on who's there. And since I can share my experiment, uh, I will show you later on. And for example, I will show you one of the experiments students has to do. So my system has some friction, which means I need to apply some voltage to the motors in order to turn. Oh, I forgot something. The aim of this module is, for example, to control the speed of at which the red triangle turns, or the position of the red triangle. So to do this, you have to identify some key parameters of the system. And to do this, you do an online experiment. So for example, here I apply zero point 0.2 volt to the system, it doesn't turn, 0.4 volt doesn't turn, zero point 0.6 it starts to turn. So it's between 0.4 and 0.6. And then I do a big step on the system, and I observe the system that it turns, but it's not immediate. It takes some time to reach this value. So here I can, for example, save save it into edX, and then I have other tools where I can get the measurement I had. So here I have the measurement I just made, and I zoom it so that you get a good view of what's going on. And what we do here, we will superpose to my measurement here I made on the system, that my system response. I will superpose this pink curve, which is a model of the system. And while I'm changing interactively this pink curve on the top of the system, my parameters here, my simulation parameters change as well. And what you'll see is that here, for example, the time constant of my system is 0.32 seconds, and my static gain is 0.8. And then these values are used for the following part of my exercise. And then I have, for example, here, okay, I don't remember, I had like 0.3, and then I can validate my thing, and then I can go to the next step and so on. So here you see that we can have remote experimentation. We have approximately 30 of these small tools here, small experiment. We have 30 of them. And then we have other interactive HTML interactive tools. Okay. And if I go back here, I'll show you. So what we implement here, we implemented the controller observer mode so that you could have two students working on the same setup, and one control it and the other one, here you see it's not gray, it's grayed out, so it cannot control it. There's the student on the left can control it, but the students on the right can see what the student on the left do. And basically that's what oh sorry, that's what has been used during this semester. So students were connected through Zoom together in groups, and they were playing interactively on a system. If the students are not working on at the same time on the system, it's also a good way to multiplex access to shared resources. So we had groups of class of 200 students and 20 system approximately. So we had a ratio of approximately 10 to 1. And with this time multiplexing, we had no problem that student access the system when they needed to. So the waiting time of the students was very little. So if they connect to a setup and they see, oh, I have one person in front of me, so they know that they have to wait probably between 30 seconds and 3 minutes to access the system and do their own experiment. We also had this continuity of interaction where we could save data within edX. Actually, it's not really edX. We have our own database on the system, but we use kind of edX authentication so that when the user save a measurement goes through the database, you could reuse it later on. Then these parameters can be saved again, used in other tools, and then you can save it and you can go with this experiment, and then you have a change of experiment and with all this data following you on the system. And these data are linked to your edX account. Okay, we've been, as you've seen, have you seen previously, we've been using this equipment for more than 20 years. So we did a lot of evaluation at the beginning, and the key point that students like it is it's very interesting to be able to do or redo the hands-on session at home whenever we want and at the pace I want. And what we see is that during the semester they're using, and like a week before the exam, we also start to see a peak of activity and students redo the TP. This year, so we had these two courses using the same hands-on session. The two courses are a bit different. The number of credit is different, but the hands-on part is the same. They use the same MOOC TP, and it was extremely positive. It's like a Russian election. So it was very, very positive. Uh, what we do normally, we take the students at the beginning of the semester, or like in share, we say, okay, every 3 weeks you can come to the lab and play with the real system. Nothing replace being close to the system. For example, we do not stream the sound, and depending on what voltage you apply on the motor, we could use a binary sequence of signal on the motor, and if you're close to the motor, it really sounds that you heard the motors. But if you do it remotely, you don't have the sound and you don't feel the problem the motor is facing. So it's always useful to be on site. And also, one thing we noted when we started to move everything on a MOOC, especially this year, we had another MOOC as a complement to the MOOC TP, and that's what I call the spoon feeding effect, that we cut a long experiment. It's such small parts and small and simple parts, so it was easy to answer and easy to select this part, but they kind of lose the overall aspect, and at the end we should add another kind of experiment where we put all these small parts together. So this is something we will be working on for the next semester, that they will have to do an experiment that is equivalent to the 3 or 4 sessions they were doing previously. And so I think, yeah, it's good time for the conclusion. So the first question you should ask when you put your setup online, so can I make my system autonomous? Do I have already measurement point, an actuation point, and do I have a client application? If not, I will need to design one. Uh, Putting the system online is one step. Then the next step is to resync your hands-on session. With the current implementation, we could easily support a 10-to-1 ratio, so 10 students for one setup ratio, because we split the system in small experiment. It took us many years to have, like, I would say, perfect, I mean, running online labs. It's not, a 1 year, or you have to plan, hardware updates, software, curriculum, everything is, you should use agile methodology to implement this. And of course, you don't have to implement this. Maybe, remote desktop access to your PC is sufficient, or recording experiment and providing recorded measurement to the student is also probably perfectly valid for the students. Closing notes. So we had open access. I mean, our setups, our MOOC is open to the outside world, which means open means everyone can access it. And on the map here, you see that the red is the invalid access and the green are the valid access. Okay, here in the center is a 00 position. That's the IP address. I could not find the geolocation. But you see that the system is constantly under, I would say, attack. So people try to get an access to the system. So they try to hack the system. So you need to have a very robust server. That's the job of the person who does it. It took us also quite some time to secure our system. Okay, like 2 more minutes, I'll show you 3 experiments that I took from the Alibaba cave, from the physics department. It's amazing. I don't know if you've been there, but they have, uh, I would say, like 800 experiments that they take and they put in class, and that they show to the physics students. They have great experiment with great teacher and great preparator. Every time I go and watch the video, so they have videos for 800 of this system. It's really amazing. um I'm very very impressed by the work they did in the physical department. So here I have one experiment.
Le faisceau laser.
Okay,
Si
I
on...
will check the Cavendish balance. And basically, here, one of the issues is that you have to speed up the time to see what's going on with the laser system. So here is typically, so it's easy. Here you have a recorded video. You can have speed up the time. It's easy. But if you want to have an interactive experience, it's complicated. So you have to either record it or allow batch experimentation or a simulation, or you have to upgrade the setup and, for example, having a longer distance so that the deflection of your laser is amplified by the distance. The issue is that here you already have an auditorium. Maybe it's more difficult to have a laser that goes like the length of 10 auditorium. Here, another example where you have these 2 cylinders. It's great experiment, but then the issue here, you have a human, and then if you want to put this experiment remotely, you have to replace the human by a mechanical equivalent. So you have to think what you need to do. So maybe it takes like a week or two to find out the system and to have the setup backup, and so you could start another experiment remotely. And here you have a system that is almost ready. So basically you're turning a knob to change the voltage of the motors and you already have the measurement. So everything is there. So here's take like 1 day to put it online. So it's just for you to give you an idea. You have things that maybe you have to reconsider to put the first experiment online. The second one, you need to think about how to replace the human, but the third one is almost ready to be put online. And that's about it. Okay, I think I'm almost done. Okay, so,
Even
oh
put
yeah,
my life on the line
that's,
to
I like
show you
this
that I'm
video.
really a believer of the conservation of energy. 3, 2, 1, 0.
Okay, this is a famous one. I find it funny. Do not forget that EPFL also has a lot of video online showing this phenomenon. I mean, the various phenomenon. It's really amazing what they have. And I've put some reference if you want to access all these things. If you want to have some software package, you can just come and talk to me. And here you have the link to the course. And there is this other link. I will, okay, why don't I? So I promise you to access the other live experiment that we use in the first one we put online. So here you have some water that comes and then you can change a dam here, the height of the dam, and you'll see there are some hysteresis and you can play with the system. And so we did many experiments to see what was the best way of doing this and sharing how do we give access. So this one is in the race mode, so that's the first one who play with the knob here can change the system, and that's the one that was integrated within the MOOC previously. Okay, I'll stop here because I think I've already took too much of the time allowed. And okay.
So
Um,
thank you very much, Christoph. That was amazing.